So this is the, okay, so then in that case, I have to repeat what I have said, because since it is a recording, I was discussing the inner product space, and in inner product space, my today's first concept is norm of the vector. So if this norm of the vector is analogous to the concept of length of a vector, and it is defined as follows: if V is the inner product space, then if for any vector belonging to V, which we denote by X, the norm is actually defined by this notation, and the norm of X is actually the positive square root of the inner product of the vector with itself. Now, for the vector space Fn, which is the set of all ordered n tuples, the vector X looks like having small n number of components, a1, a2, an. For this type of vector, the norm is calculated as follows. We consider the components individually. We take the modulus of this component, take their square, and we sum them up together, and then the positive square root is taken. This is the norm. This is how the norm is defined for the vectors in Fn. Now, for n equals to 1, the norm of X is actually nothing but equivalent to the modulus of the first component. That is only because for n equal to 1, only one component is there, that is a1. Okay. Here in this particular problem, we are considering the vector space C3, which is the vector space, complex vector space defined over the set of complex numbers, and they are triplets, and therefore the vectors looks like this. X is 2, the components of X are 2, 1 plus I, and I. Components of Y are 2 minus I, 2, and 1 plus 2I. First of all, we need to calculate the inner product X and Y, inner product of X and Y, for which we can apply the standard inner product. And we know that in case of Fn, the inner product space, vector space Fn, if the inner product is defined in the following manner, that we take the first component of the first vector and we multiply it by the first component of the second, complex conjugation of the first component of the second vector. And if in this way we keep on multiplying, and if we add them together ultimately, then this sort of inner product is called standard inner product, and under this inner product, Fn is the inner product space. Now we can apply this particular rule to calculate the inner product of the two given vectors. Here X and Y are the vectors. We are putting their structures inside the bracket, inner product bracket, and the components I'm marking as a1, a2, a3. Here the component a1 is 2, component a2 is 1 plus I, component a3 is I. These components are for the vector X, and here component b1 is 2 minus I, component b2 is 2, and component b3 is 1 plus 2I. These are the vector components for the vector Y. Now, if I apply the if I apply the standard inner product rule, then I have to take the first component 2, and then we have to multiply this by the complex conjugation of the first component of the second vector. That is the complex conjugation of 2 minus I. 1 plus I will similarly be multiplied by the complex conjugation of 2, and I will be multiplied by the complex conjugation of 1 plus 2I. Now, since complex conjugation of 2 minus I is 2 plus I, and 1 plus 2I is 1 minus 2I, we have substituted them over here. And since 2 is a real number, the complex conjugation is the number itself, so it remains same. And in this manner, we get the quantities, and after that, if I do a little bit of calculation, 8 plus 5I comes out of it, which is a number, of course, because inner product is a number. This is the length of the vector, given vector. Sorry, not length, the inner product between the two given vectors. Okay, so this is how we calculate the inner product between two different vectors. Now we are supposed to calculate the inner product between, first of all, we are supposed to calculate the inner product between the vector X with itself. So I have put the vectors in this particular manner, and now I am going to do the same thing that I have done earlier. So I am writing it in this manner: 2 multiplied by 2 bar, 1 plus I is being multiplied by 1 plus I bar, and I is getting multiplied by I bar. And Because in this particular case, although the vectors are same, we will treat the first part, that means when the vector x is written here in this position, we'll consider this to be a1, a2, a3. And when x is written on the right hand side in that position, we'll consider it as b1, b2, b3. Although in this particular case, a1, b1, a1 is equal to b1, a2 is equal to b2, and a3 is equal to b3. But for the sake of our calculation, we are doing it in the following manner. Now, this becomes 2 into 2. This becomes 1 plus I into 1 minus I. And this becomes I into minus I. And this is 4, 1 minus I square, and minus I square. And this is 5 minus 2I square, and which is 7. Okay. And by definition, the norm of x is equal to the positive square root of the vector x comma, the inner product of the vector x comma x, which is nothing but the positive square root of this number 7. So length of the vector is root 7. So this is the norm of x. Similarly, you can calculate norm of y. So let me quickly do it over here. We will write the vectors 2 minus I, 2, 1 plus 2I. This is the first vector I'm writing. Second vector is similar to the first vector. And then you can do the thing component wise. 2 minus I, 2 minus I, the complex conjugation of it. 2 multiplied with the complex conjugation of 2. 1 plus 2I multiplied by the complex conjugation of 1 plus 2I, which is 2 minus I, 2 plus I, 2 into 2, 1 plus 2I into 1 minus 2I, and that is 4 minus I square plus 4 plus 1 minus 4I square. 4 square, 2I whole square, that is 4I square, and that would be equals to 4 plus 1 plus 4 plus 1 plus 4. So how much is coming? 14. 14 is coming. And therefore, norm of y is equal to positive square root of this inner product of vector y with itself, which is root over 14. Next part is C, where we are supposed to calculate the norm of x plus y. For this, first of all, we need to calculate the vector x plus y. First, we calculate the vector x plus y. And you know, since the vectors x and y are belonging to C3, and when we add the two vectors, we add them actually component wise. So we write the vector 2, 1 plus I, and we write the vector 2 minus I, 2, 1 plus 2I, and this is equal to 2 plus 2 minus I, this is the first component, 1 plus I plus 2 is the second component, and I plus 1 plus 2I is the third component, which is equal to 4 minus I, 3 plus I, and 1 plus 3I. So this is the vector x plus y. We need to calculate the inner product of the vector with itself. So we write them in their triplet form first of all, for the sake of our calculation. And then you apply the standard inner product rule. Okay, and this is equal to 4 minus I into 4 plus I. This is 3 plus I into 3 minus I. And this is 1 plus 3I into 1 minus 3I. And if I do it, we get 4 square minus I square. That means 16 minus I square plus 3 square minus I square. That is 9 minus I square. And 1 square minus 3I whole square. So 1 minus 3I whole square. So we get 16 plus 1 plus 9 plus 1 plus 1 minus 9 I square, that is plus 9, and which is equal to 37. And therefore norm of x plus y is equal to root over 37. Now in the problem it was also mentioned that, I'm writing it over here, verify that these satisfy Cauchy-Schwarz inequality. Verify whether the vector satisfies Cauchy-Schwarz inequality. So that portion was also there in this particular problem. So Cauchy-Schwarz inequality, the derivation of Cauchy-Schwarz inequality, I will derive it in the next session. But before that, let me give you the form of the inequality so that you can at least verify whether this is satisfying or not. So Cauchy-Schwarz inequality is actually given as the following. It is very important inequality. It is given as follows. Cauchy-Schwarz inequality is given as, let V be an inner product space. Inner product space over F. Then for all xy belonging to V and C belonging to F, we have modulus of the inner product x comma y. This should be less than or equal to norm of x multiplied by norm of y. This inequality is actually called the Cauchy-Schwarz inequality. And there is only another inequality, which is called the triangle inequality, which is given as follows. I'm also writing it over here, triangle inequality. Triangle inequality we all know, but in the norm form, it is written in the following manner. The triangle inequality is given as norm of x plus y. This should be less than or equal to norm of x plus norm of y. So we can add this part also. Verify that this satisfy Cauchy square inequality and triangle inequality. Triangle inequality. Okay. Now you see, just you have calculated everything. What is your norm x? Your norm x is root 7. Your norm y is root 14. Your norm x plus y is root over 37. And norm of x comma y, inner product of x comma y is 8 plus 5i. 8 plus 5i. Now with these values, you just check whether the Cauchy square inequality is getting satisfied or not. And what about triangle inequality? Is it satisfied or not? Verify and tell me. You can unmute yourself and you can say that it is being satisfied. So modulus, you have to calculate the modulus of this. Modulus of this vector means modulus of x, inner product of x and y is actually mod of this particular term, and which is root over 8 square plus 5 square. Okay, in this manner, you can calculate, you have to just check whether the product of these two items, norm x and norm y, is greater than this item or equal to, or not. It can either be greater or equal, and here you have to add norm x and norm y and check whether it is greater than root over 37 or not. Just verify it. Is it coming?
Yes, sir.
Yeah, okay. So in this particular problem, Cauchy square inequality and triangle inequality are both being verified, and they are set. These vectors satisfy this inequality. Example 2. In a vector space, C01, let ft is equal to t and gt is equal to e to the power t. Okay, compute the inner product of fg, find norm of f, find norm of g, and find norm of f plus g. Then verify both Cauchy Schwarz inequality and triangle inequality for these vectors. This is the second problem. So my time is almost running out for the first session of today's class. In this next session, you just copy the problem. In the next session, we are going to check how to calculate the inner products and norms for this particular functions with respect to the vector space C01. And those who know how to calculate this, they can start doing the calculation. In the next class, I'm going to take the attendance. We are going, don't write anything in the chat box now. In the next session, you write it.
No, that is the good one. What do you need to find? Find from definition. From definition means we have to use the definition of U. From definition. Before 0, 0, y 0.